Hello and welcome to this video about Ethernet. I'm Wolfgang Dremmel and I usually run the DKIX Academy. You can find more videos and more content on our website. Just go to dkix.net/academy and have a look. Good. So let's get started. This whole web series is called Networking Basics, and in this series I'm going to explain various layers of the internet. I started in the first one about explaining how the layering works, and today I'm going to talk about Ethernet, and this is the whole series. So just have a look at our website or at the YouTube playlist and have a look at the other videos. So, Ethernet. A modern Ethernet device like DKIX uses in its data centers looks kind of like this. A big box connects hundreds of clients, hundreds of devices using optical interfaces with speeds up to 400 gigabit per second. But if you have a look around in your home, this is also an Ethernet device and it might sit in your basement. This is a Fritzbox and it connects 4 devices directly. It uses copper interfaces and with a speed up to 1 gigabit per second. So Ethernet has quite a range of speed and of devices. And if you think about network plans, seeing these 2 devices in the data center and in your basement, why does the symbol of Ethernet look like this? A line with other lines connecting to it. So let's go back in time. Let's go to the year 1971 and let's go to Hawaii. In 1971, the University of Hawaii had a problem. They wanted to interconnect their campus, and their campus was distributed over a number of islands. So they invented a radio-based network. Radio means commercially available small radio transceivers, and they used that to interconnect their sites. Well, talking about a network in these days, it was really slow compared to what we have today. This network had one very simple principle. So if you have data to send, just send it. And if you receive something while sending, stop and try again. So this was the simple principle of the AlohaNet of the University of Hawaii. Let's go forward 2 years and let's go to the Palo Alto Research Center of Xerox and to a man named Robert Metcalfe. The Palo Alto Research Center of Xerox brought us quite a number of inventions. For example, the mouse you are using was also invented there. And in 1973, Robert Metcalfe had the idea, instead of using radio, to use a coax cable. That had quite some advantages, like he could do higher bandwidth and also it was way more reliable. But the idea transmitting on a coax cable was inspired by AlohaNet. The whole setup was standardized first in 1980, then as Ethernet 2 in 1982, and then at IEEE 802.3 in 1983. And this is basically what we're still using today. So how did this early Ethernet look like? The devices they used were a coax cable and transceivers. And this early Ethernet was named 10BASE-5. It had a speed of 10 megabits per second, which was incredibly high speed at this time. It used baseband modulation and it had a maximum length of 500 meters. The hardware they were using was a very thick, a 1 centimeter thick yellow coax cable and so-called vampire tap transceivers. So how did it look like? Let's go back to our network drawing. The vertical line, This is the yellow cable you just saw. It's a coax cable, and you are using vampire tabs. Vampire tabs were clamps to this cable, and they drilled in and attached to the middle of the cable, and this was then a transceiver, and this was how a host was connected to the Ethernet. Quite different than today. Forward a few years, 10BASE-2. It was still only 10 megabit Ethernet, but it used a simpler cable and it used plugs instead of vampire tabs. These BNC connectors were used, and if you are as old as me, you might remember them. The 10BASE-2, because the maximum length was 200 meters, it was also called CheaperNet, and it was in use from the mid to late 1980s. Next version of Ethernet was called 10BASE-T. It was still 10 megabit, but instead of a coax cable, they were used these twisted pair cables. At the beginning, just with 4 wires, later with 8 wires. Since 1988, this slowly replaced the coax cable. Disadvantage or advantage was that it needed a central device. It needed a switch to connect to. No longer running a coax cable on the floor and going under your table to check for errors, but now you had twisted pair cables connecting each computer to a central device. But Ethernet wasn't the only standard in these days. There also was Token Ring. Token Ring was invented by IBM, and they had a patent on it, and if you wanted to use it, you had to pay license fees. The speed of Token Ring was first 4 megabit per second and later 16 megabit per second. That sounds less, but Token Ring had what some people saw as an advantage. It had a deterministic access mechanism. Remember, Ethernet, send when you have something to send. If someone else sends, wait a random amount of time and then try again. Some people thought I might never get to send my data, which of course didn't happen. Token Ring guaranteed that you could send data in a fixed or in a specific amount of time, because it used a token to be passed around from system to system, and when the token arrived at a certain system, this box could then attach its data to send to that token, send it along. Of course, that was way more complicated than Ethernet. It was more complicated to cable, and it also needed some multi-station access unit, and it was also more expensive. So it fell into disuse in the 1990s, but guaranteed there are still some installations out there. A kind of a successor to Token Ring was called FDDI, and FDDI was the first network which only relied on fiber network connections. Instead of one ring, it used 2 rings for redundancy. It had a speed of 100 megabit per second and could be 200 kilometers by size because of fiber. Also, the frame size was higher than Ethernet. Ethernet used a frame size, or still uses a frame size, of 1500 bytes. FDDI used 4352 bytes. But also, again, it was expensive, and it was replaced by gigabit Ethernet later. Let's go back to Ethernet and keep remembering where Ethernet comes from. Ethernet is a broadcast network, and all stations are connected to a shared medium. In the beginning, a coax cable, later, well, kind of a virtual shared medium in form of a central device. Broadcast network means that one station is sending and everybody is receiving it. So all stations share one medium, and only one station at a time can send. If 2 stations send, a collision occurs, and that can be detected by the senders, and then they both stop and try again after a random amount of time. And yeah, mathematicians don't like randomness, so this was seen as a disadvantage of Ethernet, that there was no guaranteed delivery. But well, what you're using today, you're using Ethernet, so somehow it works. Good. Broadcast network means one is sending, everybody is receiving. Everybody is receiving everything, even packets or even frames which are destined to another station. So how to avoid overload and unnecessary data processing? Well, the idea is each station has a unique 48-bit address, and this address is the beginning of each frame. And the address can be processed by your network card. It doesn't have to be passed on to the CPU. If your network card detects this frame is not for me, they can simply throw it away without bothering the CPU. So this keeps CPU load low, and it works. So only frames with a matching address or broadcast frames are forwarded to the CPU. But how does an Ethernet frame look like? I already mentioned that it has addresses, but it starts with a so-called preamble, and this comes from the radio days, because the preamble is simply 101010, and it ends with 11. As soon as a station receives this 11, that means attention, an address is following. So next is the address, the destination address. A receiver must check if this matches its own hardware address. The address of an Ethernet card is built in hardware, usually. Then we have the source address, that's the Ethernet address of the sender. Then we have 16 bits called an ether type. Ether type tells the CPU, the network stack, what kind of payload this Ethernet frame contains. Is it IPv4? Is it IPv6? Or is it something else? So that's coded into the ether type. And at the end, we have a checksum. Talking about Ethernet addresses, like I said, we have a destination address, we have a source address. These addresses are 48 bits. That's 6 octets long. So that's quite a lot of addresses available. And this address space is managed by the IEEE. And if you're a hardware vendor and you are building Ethernet cards, you have to purchase blocks of addresses to burn into your Ethernet hardware. Notation example of Ethernet addresses, well, it looks like this with the colons, or you can also use it with dots or with dashes. All are equal. The most common one is the first one. There are also 2 bits in the Ethernet address which have a special meaning, and this is called a global versus a local address. So you can also have local self-assigned Ethernet addresses if you set this bit, and you have a unicast multicast bit. Unicast means one station is a receiver. Multicast means more than one stations should receive this Ethernet frame. There's a special multicast address, and that's the broadcast address where all bits are set to 1, and that's received by all nodes on an Ethernet segment. The payload here is an example to some payload types like IPv4 and IPv6. If you want to have a look what payload types exist, at the end of the slides, if you download the presentation, you can find a link to a table of ether types. That was the history of Ethernet and how it came into being and how it works. Now let's have a look at Ethernet today. Today in a modern data center, usually optical fibers are used. And there are different kinds of fibers called single mode, called multi-mode, but they all have in common that light is used to transmit Ethernet frames. Speeds of modern Ethernet are 1 gigabit per second, 10 gigabit per second, and up to 400 gigabit per second. Remember, it started with 10 megabit per second. And the connections in Ethernet today are between a switch and an end device. I'm talking about switches later. Ethernet at home. Usually you use copper because it's easier to handle, and the speed you have at home is either 100 megabit per second or most commonly today 1 gigabit per second. Also, there is wireless Ethernet. It's extension kind of. It uses, of course, your Wi-Fi to do that. Let's have a look at Ethernet at home and how it started, how we migrated from the yellow coax cable to what we have today. At the beginning, remember, vampire taps and a coax cable. But 10BASE-T required a central device, and so the first central devices were called hubs, and they simply replaced the coax cable one-to-one. So everything which was received on one port was broadcasted on all other ports. And just like the coax cable, but with twisted pair ports. Today, a switch is used. And a switch is an intelligent device, and it learns on which port which Ethernet end device is receiving. So it only sends out frames through ports where the receiver is, and it learns that by listening into the source Ethernet addresses of frames it receives. If it doesn't know where it is, well, it falls back to the old behavior and broadcasts or floods. We call that flooding. It sends out the frame through every port. But well, Ethernet still today has a maximum payload of 1500 octets. There is a definition of so-called jumbo frames with 9000 octets, but it's not very often used. We're still using 48-bit Ethernet addresses, and Ethernet is still a broadcast medium. Also, most commonly, switches are used, and the connections are nowadays point-to-point from an end device to a switch. If you remember from the last presentation where I talk about the layers, Ethernet sits on the link layer. Data units are called frames. And remember, the purpose of the link layer is to provide node-to-node data transfer. So from here to the switch and perhaps some to the basement. Conclusion. Please remember from today's presentation, Ethernet is a broadcast network. It uses 48-bit long addresses, which are globally unique. Ethernet frames have usually a maximum payload of 1500 bytes, and today switches interconnect devices. And that's it. And thank you for listening. And I hope that you watch my other videos. Just go to the DKICS website, search for Academy, or have a look at the YouTube playlist. I'm Wolfgang Kreml. Thank you and bye-bye.